how the heck did the planet survive? It could have been ejected from its system. It could have, been swallowed up by the red giant. Just the fact that the planet is there tells us that something remarkable happened in that system. So this planet, WD1856b, is 8 times larger than the star it's orbiting. And that's just so weird to get your head around. I got together a team, we wrote a proposal for the James Webb Space Telescope, and we were awarded time.
Hello and welcome to another episode of Becoming Multiplanetary. On this episode, we're going to show you the second half of the interview we had with Dr. Ryan MacDonald. So without further ado, let's just get right into it. So, moving on to the white dwarf opportunity, we had the chance to speak to you prior about this. I'm really excited to talk about this. And first of all, I'd like to announce that I've successfully memorized WD1856b's name.
We can make it harder. That's the shorthand. The full name is WD1856 plus 534b.
I did see the plus, and I was wondering whether that's actually it was just if it was a more full designation. But yeah, man, I kept forgetting the name of this star, and I'm like, it's really weird because the story of its star itself is very interesting. And Ryan, why don't you tell us what's so interesting about WD1856b?
Sure, absolutely. So WD1856b is the first transiting planet we have seen around a white dwarf. So white dwarfs are, you can also consider them, sometimes we joke and call them zombie stars. So you have a star just like our own sun. Eventually, the sun is going to die. It will expand, it will become a red giant, and our star doesn't have enough mass to go supernova, so it will kind of just whimper and throw off its outer layers, and the leftover core of our sun will become a white dwarf. So this will be the fate of our own solar system one day. So white dwarfs, they're glowing balls of kind of like oxygen, carbon, maybe a bit of neon and things mixed in there. And they still shine, not because of nuclear fusion, but kind of from the residual energy just left over from when they were a star, and they just gradually cool and contract over time, shining for, longer than the age of the universe. White dwarfs are going to be around for a very long time until they're not visible anymore. So, simply put, a white dwarf is just the core of a dead star. So finding a planet around a system like this is incredibly exciting, because on both a kind of a poetic level of, we want to know what happens to planets after their stars die, because it's going to happen to our own solar system someday. And how the heck did the planet survive? It could have been ejected from its system. It could have, been swallowed up by the red giant. Just the fact that the planet is there tells us that something remarkable happened in that system. And I should say that this planet, it orbits 50 times closer than Earth does. So this is way closer than Mercury. So this is a planet about the size of Jupiter. And the truly weird thing about this system is that white dwarfs are really small. They're just this clump of degenerate matter about the size of the Earth. So this planet, WD1856b, is 8 times larger than the star it's orbiting. And that's just so weird to get your head around. So when we see a transit happen, we see half of the light from the star just vanish when this giant planet just sweeps across the surface. It doesn't block out all the light because it's kind of like at an angle slightly, so it just kind of the north part of the planet kind of sweeps across the star. But that's enough to block out half of the star's surface. So it's a truly, truly weird system. And it was announced last year, September of last year, if I remember correctly. So it was found initially by the TESS mission, NASA's New Transit Survey. But then because half of the light is blocked, it was very easy to confirm. The Spitzer Space Telescope was pointed at it, but small ground-based telescopes run by amateurs in some cases were just contacted via the science team if they had a friend with a telescope. They pointed at this star and just saw that half the light was disappearing every 1.4 days because it's so quick for the year on this planet that it was very quick to confirm that this planet is there, and it's a truly weird and remarkable system. And so what I'm excited by it, so when I heard this planet existed, I very quickly started thinking about ways that we could characterize this planet, and I got together a team. We wrote a proposal for the James Webb Space Telescope, and we were awarded time. So in the first year of James Webb observations, we're going to actually look at this planet 4 times to obtain a high-quality spectrum of the atmosphere of this planet, and we're hoping to detect multiple gases that can then tell us about the story of this planet. How did it get to where it is today? How did it survive the death of its star? And because this planet looks like perhaps it's just an older cousin of Jupiter, what will that tell us about our own fate in the future? So I really can't wait to get those observations.
Very exciting.
There's going to be some really nice stuff to see there, I bet. And if you do come up with a good theory of how exactly 1856b survived, then I would definitely love to hear it.
I mean, there are 2 main theories. We don't know which one is right. One is that when the star expanded into a red giant, the planet, which would have been about as far out as Jupiter is, actually was just kind of gobbled up by the very outermost layers of the red giant. And then friction started to cause it to spiral inwards. We call this a common envelope evolution. But just before the planet was gobbled up by the star itself, kind of all the gases were dispersed, and it was left kind of just clinging on to life quite close to the star. The second scenario, it's called something called the Kozai-Lidov effect. There are kind of 2 nearby stars close to the system, and over many, many millions of years, their gravitational influence could have kind of nudged the planet and caused its orbit to like wobble and very gently spiral in over time. It's like the orbit of the Earth is wobbling all the time from the influence of the other planets. There are things like Milankovitch cycles and things that very gradually change the climate over tens of thousands of years. A similar thing could happen in this system, but cause the planet to migrate in. We don't know which answer is right yet, but we are planning lots of observations to try and break this uncertainty and figure out how the planet got to where it is today.
So here's a kind of a different question. We can see a lot of planets, and we have a lot of examples where the plane of the orbit is kind of pointed at the Earth. Do we have any examples where that's not the case, where we're more top or bottom viewing?
Yep. So you're absolutely right that when we detect transits, they have to be, the plane has to be aligned. It doesn't have to be a perfect alignment, but it has to be like within 1 or 2 degrees of a perfect alignment. Radial velocity planets, this Doppler effect, you can see any angle apart from when they're perfectly perpendicular, because then the star would be going up and down and we wouldn't see a redshift and blue shift. So many radial velocity planets don't transit. And directly imaged planets, of which we found, I'd have to remember the number, I think it's like 50 to 100 at the moment. Many of those are not aligned right. So yes, we do have examples like that. And so we're in a weird period at the moment where most planets that we found are transiting, even though it's rare for a transit. It's like a 1% occurrence for many systems. But we know there will be many more planets that we will be able to directly image in the future that didn't happen to be lucky enough. Actually, Proxima Centauri b would be one example. That's not aligned and right to transit, but we know it's there because of its radial velocity Doppler signal.
We have a question from Miko in chat, and it deals with 1856b, actually. He's asking, if you're successful in detecting its atmosphere, do you expect to get more view time, and possibly for other white dwarfs? And how many planets do you expect that will be close around white dwarfs? So
that's a really great question. And when I was writing our observing proposal for James Webb, we had to think very carefully about how much time we were going to ask for. There's like a cost-benefit analysis. Because obviously you want to get as much time as you can, but if you ask for too much time, they might just say, come back to you and say, you asked for too much time, next year propose a reconnaissance program, and then we'll see if you need more time later on. So I ran computer simulations for what we could learn about the atmosphere from 1 transit all the way up to 10 transits. And I concluded that the sweet spot would be about 4 transits. Because if you observe a single one, since we don't know anything really about the atmosphere, in fact, we don't even know the mass of the planet, we just know how large it is. The larger the mass of the planet, gravity kind of compresses the atmosphere, and that means you need a lot more transits to be sensitive to the atmosphere. So because we didn't know the mass, I had to kind of hedge bets a little bit and say, with 4 transits, we are guaranteed to detect water, not water, it was ammonia, methane are guaranteed, and maybe water, if the planet is about the mass of Jupiter, and actually maybe phosphine. This wouldn't be biological phosphine, this would be the natural phosphine we see in Jupiter's atmosphere. So 4 transits I thought was the sweet spot. If it turns out when we get those observations that they weren't precise enough, or there was an error, or just it wasn't quite good enough to achieve our science goals, then absolutely we could put a proposal in a future cycle. And many planets that we've observed with Hubble, you first discover a planet, you ask for like 1 quick transit to observe the atmosphere and see if it's cloudy normally, because clouds kind of wash out all the features. And then you can ask for more time later on once you have some ground truth for what the planet is like, and you know how much more time you need. And you always have to justify and prove in the proposal why you need the amount of time that you're asking for to achieve your science goals. So we may very well go back. And there actually is a second program that I'm collaborating on with Andrew Vandenberg, who discovered the planet, to also observe WD1856b. But we're going to look at different phenomena. I'll be looking at the light going through the atmosphere. He is going to be looking at thermal emission from the night side of the planet. So both of them are completely complementary programs, and we'll be sharing our data with each other to figure out what's going on. The second part of Miko's question about looking for planets around other white dwarfs. So Andrew Vandenberg actually has a test program that is looking at 10,000 white dwarfs at the moment to try and find more planets. So if there are more planets, and I'm really hoping there's a rocky planet, we'll find them. We'll find them soon. So, but none other ones have been found yet, as far as I'm aware.
And then this brings us nicely to what is it about those methods and working on rocky planets around white dwarfs? What is it that gets you so much more from that?
Yeah. So the key thing is that we call it the small star opportunity. The smaller a star is, when a planet passes in front of it, the atmosphere of the planet blocks out a greater fraction of the surface of the star. So if you just take the Earth, for example, in front of the sun, we would not be able, even if we knew a transiting Earth and we looked at it, the signatures of the atmosphere of the Earth would be so weak that we just don't have the technology to study it at all at the moment. But if you just take the Earth and move it around a red dwarf or M dwarf star, then this is examples like the TRAPPIST-1 system, where we are on the threshold of being able to characterize those atmospheres. James Webb will be able to study those atmospheres, and I will be involved in efforts to analyze those early observations from James Webb, of TRAPPIST-1e in particular, but I have colleagues who will be looking at the other planets in the system as well. So what we thought is, can we do one better than M dwarfs? So an M dwarf is 10 times smaller than the sun, and it turns out that the strength of the atmospheric absorption goes like the square of the size of the star. So 10 times smaller star, 100 times stronger atmospheric signatures. But a white dwarf is 10 times smaller than an M dwarf, so we get another factor of 100 boost compared to even promising planets like the TRAPPIST-1 system. So if there turns out to be a rocky planet transiting a white dwarf, the signatures of the atmosphere will be so strong that we will be able to very rapidly study the atmosphere. And to put some concrete numbers on that, we really want to detect biosignatures in exoplanet atmospheres. It's what got me interested in the field, and it's what I'm going to be working on. But even with James Webb, it's going to take a lot of time, even if a planet was exactly like Earth, to detect a biosignature. So I had a paper out about a month or so ago where we modeled TRAPPIST-1e to calculate how long it would take us to detect ozone and methane, a classical biosignature pair. And methane turned out to not be that bad. You could do it in about a year of James Webb observations. So TRAPPIST-1e transits every week. So every week for a whole year, you'd have to turn James Webb and observe the planet. But we found for ozone, you'd need about 5 years of observing every single transit. Because unfortunately, the wavelengths where ozone absorbs, they're right near the edge of where James Webb is sensitive. So it absorbs very strongly in the UV, where James Webb can't see. It absorbs reasonably strongly in the visible, where James Webb can only just see. And it has a really strong feature in the mid-infrared, where James Webb is less sensitive. So we're just kind of a bit unfortunate with where ozone happens to absorb light. But if we have a planet around a white dwarf, instead of 5 years of observations, it would take us 2 weeks of observing transits to get a completely conclusive detection of ozone and methane. And if you throw in a few more weeks, you can even detect other things like oxygen and even molecular nitrogen. So the white dwarf opportunity is that we can very rapidly survey a wide number of rocky planets. If they exist, we haven't yet found one, but we can do very quick reconnaissance of rocky planets with James Webb and get very precise measurements of what their atmospheres are made of. All we need to do is just find rocky planets around white dwarfs, and then we can realize this vision. We haven't found any yet, but we're looking for them.
Right. Well, yeah, having that, it's really important that, you've got a factor. Theoretically, it's a 200 factor improvement of detection. And with that, it means...
Oh, well, compared to the Earth, it's 100 times 100, so it's a 10,000 times improvement.
That means that it puts it well within the boundaries of our current technological capabilities, which is the really important part, or the takeaway of this, is that this is stuff that we have the technology to look at right now.
Or we will when it launches in November.
Yes, definitely. Speaking of which, Joe, are you looking forward to that JWST launch?
Yes, JWST is going to be very, very fun to watch and very exciting to keep an eye on. There's so many great things about JWST. It's going to one of the Lagrange points, which we don't use a ton. We launch a lot of stuff into space, so there is a lot of stuff at various L points, but we don't. We're usually in some sort of LEO or a geostationary orbit. So when we use these L points, it's a little bit more exciting because it's a little less common. So even just that part of it is quite exciting. And to watch this thing start sending back data is going to be very fun. Like Ryan was mentioning earlier, a lot of the data is open source, so people are going to be able to put things together. I mean, over time, not at the beginning, but later on, the data becomes open source, and you just get everyday people sitting looking at data and going, "Oh, hey, well, what's this little detail here?" And then it opens up whole new pieces of information for everybody to look at. So the whole thing is very, very exciting.
Yeah, some data will be released immediately. It depends on the program. So large programs with James Webb have 0 proprietary period, so they're immediately publicly accessible. Smaller programs like my White Dwarf one, there's a 1-year proprietary period, which gives us time to actually analyze the data and get it out there. But you're waiting a year and then the data becomes available. I should say, in terms of the timeline, after James Webb launches, it'll be a 6-month commissioning period before we start getting any scientifically useful observations. And but we have a special program that we call the Early Release Science Program, where the whole community, there are early release science programs in different fields of astronomy, but in exoplanets, we have 2 programs. one for people doing transiting science like myself. Everyone has got together. We have 3 planets we're going to observe. And the idea is, since it's a brand new instrument and we won't necessarily know exactly how to deal with, I don't know, if one of the mirrors gets like shook a little bit, like during launch, there could be things that we don't expect to deal with. So everyone will work together to figure out those instruments, produce a combined analysis of the first 3 planets, and then publish it together in a special edition in a journal, just like is often done in the solar system for like first results from InSight, for example. And then after that, then everyone splinters off and does their own thing, once we've at least agreed a common understanding on how to analyze James Webb data. So you can expect probably the first published results, and hence press release and interviews, and we explain what we found, probably about January 2023, just because of it has to launch, it has to unfurl, it has to be commissioned, we have to get the data, and then we have to spend 6 months analysing it and figuring out the results. So probably early 2023 we'll announce the first results from James Webb observations of planets.
It's really good that you have that as a community to be able to effectively get all one in together so that you know that the equipment works fine, that there's no... The more important thing is, as you say, if one of the mirrors shook, it would throw off everyone's data set. So if you capture that, then that means you can compensate for it in future data sets. And it's a really great idea. Really love it. And before we wrap this up, there are 2 future projects that I'd like to talk with you about as well. The first one is Breakthrough Starshot, what this means for exoplanetary science.
So, I remember when I was growing up, I loved sci-fi. Like every film, book, everything I could grab my hands on. And almost all sci-fi is set, in other star systems. There are warp drives and there are ways to travel around a galaxy. But when you think about actual, real interstellar missions, they've always seemed so far off. It was always, that's a 22nd or 23rd century thing. Because of, without the invention of something like a warp drive, we don't even really know if it's practical on an engineering level. We have to deal with relativity, and we have to deal with the huge spaces between the stars, which even for missions like Voyager will take 70,000 years to get to a nearby star. So when Breakthrough Starshot was announced, and so for anyone who doesn't know it, the basic idea is miniaturize a probe down to about 1 gram and then accelerate it to 20% the speed of light using an array of lasers reflecting off a solar sail. And then you can get to the nearest star, Proxima Centauri, 4.2 light years away, in about 20 years. And that's great because that's within the lifetime of a mission team. We don't have to wait hundreds or thousands of years to get to a nearby star. And it was funded initially by Yuri Milner, giving a grant of $100 million, mainly to fund theoretical studies behind the design, just to see if it's actually possible. Because if you wanted to apply to get funding to study an interstellar mission before, there was almost nowhere that you could apply. Charitable foundations, or if someone donates, that was the only source of revenue, because it wasn't seen as something serious that could be done within a short time frame. So I was incredibly excited when Breakthrough Starshot was announced a few years ago, because although the technology isn't quite ready yet, they are funding the necessary steps to make it be ready about 20 years down the line. So many theoretical studies I've seen have gone up online answering practical questions like, does the solar sail degrade over time due to interactions with hydrogen in the interstellar medium when you're traveling at 20% the speed of light? The answer turns out to be a little bit, but it's a problem that you can mitigate. Lots of the conceptual questions are all being figured out right now with seed funding from Breakthrough Starshot and the Breakthrough Foundation. And there are still things that still need to be worked on, like the energy of the lasers and how you transmit information back from the star system that you're at, given that you've just got a 1 gram probe that you're trying to cram a lot of hardware onto. So you might end up sending kind of swarms of these probes that then if some are lost, it's not a problem, and they kind of all network together to send fragments of a photo back. So the idea that we might live to see, maybe 2060 timeframe, a photo coming back from an exoplanet is absolutely mind-blowing. And it's a logical next step. So I see my own research as kind of it's part of a story. You know, it stretches back centuries from looking at weird stars in the nighttime sky wobbling and calling them planets, but not really knowing what they were, literally wandering stars, to then the image of the telescope, looking at planets, seeing what they're like, then looking at exoplanets a couple centuries afterwards, starting to figure out what they're like, and then ultimately the goal of the next few decades of my career will be to look for habitable planets, figure out if they are hospitable and what these worlds are actually like. We can then draw up a candidate list, and hopefully some of them will be near enough that we can start sending interstellar probes to. And, you know, my career is just one step along the journey that will eventually lead to full-blown interstellar missions going to these planets and seeing what they're actually like. So it's just amazing to be part of that journey that eventually leads to the science fiction future that we're all hoping for.
Hi there, guys. It's another Space Nut here. Sorry to interrupt this show, but if you enjoy what you're seeing, consider supporting us on Patreon at patreon.com/totalspace. I'll let you guys get back to the show.
Yes. That sounds like a very ambitious program. And when we were speaking the other day, you clued us into an even more ambitious program, and this one uses one of my favorite physics tricks is gravitational lensing. Do you want to tell us about this project a little bit, maybe?
Absolutely. So this is an idea called the Solar Gravitational Lens Telescope. And it exploits a cool effect from Einstein's general relativity that you mentioned, gravitational lensing. So a strong gravitational field bends rays of light. They are deflected when they go around a strong gravitational field. And you'll have probably seen that if you've ever seen the film Interstellar, for example, with the visuals of the black hole with the weird accretion disk that looks like it kind of is going around and above the black hole. It's actually just going around in one plane, but the light is kind of deflected over the black hole. And so it looks like it's coming from multiple places. So gravitational lensing is used all the time to study galaxies, for example. And it lets us do two things. Firstly, if you have an object that's really far away and you were just to look at it, it would be really dim. But if there is an object in between us that focuses the light from the distant object towards us, we see rays of light that would not have reached us otherwise. So the distant object is magnified in brightness. So we can then see things that are further away just because they're much, much brighter from this focusing of light beams. So the idea of the solar gravitational lens is to use our sun as a telescope, if you will, as a lens to focus light towards us. So there's a sweet spot 550 times further away from the sun than the Earth is. So 550 AU, which is a really long way away. It's like Voyager 1, I think, is at 150 AU at the moment. So it's about 4 times further out than the Voyager missions. But if you can get a telescope there, you can focus light from an exoplanet around the sun, and it amplifies the light from the exoplanet by a factor of 10 to the power of 11. So what this means is that even though you have a 1 meter size telescope, you can actually directly image the surface of an exoplanet. So you could produce a pixelated map of what an exoplanet actually looks like with something like maybe like 200 pixels by 200 pixels. But that would be enough for you to be able to say, oh, there's continents and there's a giant river delta system there, there's an ocean there, maybe, and get different spectra of different regions and be like, oh, that green patch has some weird features. I wonder if that's vegetation, or that looks like a desert. So this telescope, if you wanted to just build a telescope that could image an exoplanet normally, you would need a telescope that is 90 kilometers wide to get a single pixel of an exoplanet. And to spatially resolve it, you're talking a telescope the size of the distance between the Earth and the Sun. It's just not something that we can really build. Or you can build a 1 meter size telescope, slingshot it around the sun to get an acceleration that will boost you out. And then about 30 years later, if you use the most powerful, think a really light telescope on top of like SLS Block 2, blasted at the sun and doing a slingshot around the sun. And then you could get out there in about 30 years and then start getting photographs of exoplanets. And so the cool thing there is that although something like Breakthrough Starshot could give you a flyby of a nearby exoplanet within about 20 years, if you want to say, if we find that there's an Earth-like planet 100 light years away, just Breakthrough Starshot wouldn't really help us there. But we could use this solar lensing telescope to continually take photographs and spectra of an Earth-like planet 100 light years away and see how its weather changes over time. It's not a one-time thing like a flyby. So it's part of the logical progression. Find planets that are Earth-like, see if there are hints of habitability with James Webb, use a future mission like LUVOIR to look at it, to do a survey of nearby habitable planets to draw up the short list of the most promising ones, launch the solar gravitational lens to take photographs of what these habitable planets look like, and then we know the nearest habitable planets that have life on them to the Earth. And then we can start turning it from interstellar missions from dreams into just engineering challenges as to how to actually get them once we know where the planets are.
The only thing I think I would be worried about there is how to get that data back from the telescope at 550 AU.
Oh, it's much easier to get it back from 550 AU than from Breakthrough Starshot. So you can have a larger antenna on a 1 meter telescope. So that should be less of a technical challenge.
Yeah.
Because we're still hearing back from Voyager. Fine at 150 AU.
Yeah, I think it's something like 4 kilobytes a second they can downlink at, or something like that.
We've got slightly better technology since the 70s, so I think we'll be fine.
So that about wraps it up for today, I believe. So Ryan, thank you very much for coming on and having this chat with us. It's been amazing.
Thank you very much for the invitation to speak to you all. If anyone is not aware of my own YouTube channel, which I have myself, Martian Colonist, I make videos on there both about exoplanets, like we've discussed today, and also about sending humans to Mars in the future. So feel free to check me out if you're interested.
Absolutely. And in fact, I have a personal recommendation. You should definitely check out his latest Mars mission update. That was an absolute inspiration to watch. So if you want to watch something, watch that first.
Yes, it was very well done video. Very well done video. All right. Well, so what do you think, folks? Do you think we'll find evidence of a second Genesis? Or maybe you think we're truly alone here in the cosmos? Let us know in the comments below.
From those of us here on Becoming Multiplanetary, I've been Rich LB.
I've been Astro Odie.
And I've been Ryan MacDonald.